Welcome back to Physics 371. We're going to extend our treatment of magnetic materials to talk about a specific kind of magnetic material, which actually is very common, and that is a linear magnetic material. So in paramagnetic and diamagnetic materials, the magnetization is caused by some kind of applied field, H. And if the field's not too large, the magnetization is usually directly proportional to the field strength. And so we write this M as equal to a constant chi sub m times h. And chi sub m is called the magnetic susceptibility. And it's a parameter that characterizes a particular kind of material. Note that this differs a little bit from the relation that we came up with for dielectric materials when we were looking at how an applied electric field causes a polarization or a reorientation of the charge in a dielectric material. P we defined at that time to be equal to epsilon naught times chi sub e times the electric field. And the difference is not only that there's this epsilon zero term here in the case of the polarization equation, but rather that the polarization equation has P proportional to E, where E is the total field. And I've always thought that this is kind of a strange definition. We have it for historical reasons, but I think actually the relationship between the magnetization and the applied field H makes more sense, because H is directly the applied field that one generates in the laboratory, let's say by running current through a solenoid and putting a sample inside the solenoid. That sample then gets magnetized according to this relationship here. So chi sub m, as I mentioned, is called the magnetic susceptibility. It is a measure of how susceptible a material is to being magnetized by some kind of applied field. And here we have a little bit of a difference, because in the case of magnetic materials, we've already talked about how you can have either the magnetic dipole moment interior inside the material line up with the applied field, in which case you have a paramagnet, or you can have the net response being the internal magnetic dipole moments being aligned opposite to the field, and that's diamagnetic behavior. In practice, there are many materials that have both of these kinds of responses, and the question is simply which one is larger. That will determine whether the material overall is a paramagnet or a diamagnet. And you might wonder about the approximate size of chi sub m. And it turns out for most normal paramagnetic and diamagnetic materials, chi sub m is somewhere on the order of 10 to the minus 5 to 10 to the minus 6. Quite small, which tells you that normally this is a very small effect. You will have a homework problem where, using some of the discussion that we came up with when we talked about diamagnetism, you will estimate the diamagnetism, the diamagnetic susceptibility, for a copper sample. And you'll be able to come up with something simple, a simple model, and test to see whether it gives reasonable agreement with the experimental value for copper. And it turns out that copper, as I think we mentioned in class, is diamagnetic. So, back to linear materials. For a linear material, what we can do with this expression for the magnetization is substitute into the relationship between B and H that we have written down, that came from the definition of H. So B is mu naught H plus M. We're going to substitute in for M so that we have mu naught H plus chi m H, and we can factor out the H and write this in the way that it's most commonly written. B is equal to mu naught times the quantity 1 plus chi sub m times H. And there's also another way of writing this equation. If we simply write this as B, showing the direct relationship between B and H, what we do is define a term mu, which has the same units as mu naught, but actually has the value mu equal to mu naught times 1 plus chi sub m. Something I should have mentioned earlier is that chi sub m has no units, because it's dimensionless, because m and h are measured in the same units. So anyway, mu in this equation down here is referred to as the magnetic permeability, and you can either talk about the permeability of a material or you can talk about its susceptibility. One of them implies the value of the other. Compare this to the kind of definition that we made for dielectric materials, where we defined something called the permittivity, epsilon, which was epsilon naught times 1 plus the dielectric susceptibility. And so these two equations are quite similar to one another. All right, well, what's the whole point of this? Well, now for a linear material, we can use the techniques that we've already learned to find B even more easily, at least in the cases where symmetry permits us to find it easily using Ampere's law. So all we really need to know is the free current that flows through a sample or near a sample, and we have to know its magnetic susceptibility or permeability. And so if the symmetry of the current is high, we can carry out the solution to find B inside the material by first just using Ampere's law to find H. Right? That's the way that we've done it before. There are cases, of course, where H is equal to 0 if there are no free currents. But find H, which is the applied field, and then we can calculate B directly from H. And this is the important difference now, because we now have this relationship for B in terms of H. Once we find H, we've got B, at least if the material is linear. And the point is that we could, if we want to, calculate the magnetization. But there's no need to worry about it at all, because the relationship between M and H is such that we can get this simple relationship between B and H. So that's really all there is to it. Linear materials are very simple to handle, and so I'm going to post an example problem where I show you how to use this method to find the B inside a magnetic material.